So I want to take today to finish up Chapter 3. And Chapter 3 really is, Chapter 3, pardon me, Chapter 6, Part 3 of Chapter 6. Chapter 6 really is a potpourri of various functional group interconversions. And what I've tried to do in talking about the chapter is organize it conceptually into the idea of oxidation state. So carbonyls, aldehydes, and ketones, and alcohols have sort of at two levels of oxidation state, at two intermediate levels of oxidation state, become linchpins in synthetic organic chemistry. And we're going to see that as we move into chapters 7 and 8 and start talking about carbon-carbon bond forming reactions. So carbonyls are really, really important. Alcohols are really, really important. And so what I want to do today is to take some reactions that kind of go vaguely in the theme of alcohols and ketones and aldehydes, particularly ketones, and focus on some stereochemically and mechanistically interesting reactions with the idea of really bringing in advanced concepts of stereochemistry, advanced concepts of mechanism. So hopefully what I'm going to get to do today is talk about 4 different things. I want to start by talking about acyclic stereochemical control in reductions and addition of nucleophiles. We got a context of this in the last lecture for cyclic systems where we looked at cyclohexane, cyclohexanone. I want to show you these same concepts in an acyclic manifold. This is what you would call substrate-directed stereochemistry. I want to touch briefly on reagent-directed stereochemistry and reductions. Then I want to take 2 important mechanistically interesting reactions that fit into the framework of carbonyl and alcohol chemistry. One of these being the Mitsunobu reaction, and one of them being the Barton-McCombie reduction reaction. And these give rise to us thinking about arrow pushing, curved arrow mechanisms, free radical mechanisms, free radical chains, and just reinforce some of the concepts we've been talking about. Okay, so to begin, I want to show you a landmark experiment by Donald Cram. Donald Cram won the Nobel Prize in 1987. And in 1952, Donald Cram reported, and of course his students reported, he was at UCLA, by the way, very nice fellow, very interesting fellow. I met him just before he died. Anyway, Donald Cram asked a very simple question. What is the stereochemical course of reduction when you already have a stereocenter in the molecule? And so here I show a molecule of, we'll call it 3-cyclohexyl 2-butanone. It might have a different name. And we get 2 diastereomeric products, one diastereomeric product in which the cyclohexyl group and the alcohol group are on the same side of the ring in this reduction, are on the same side of the chain, and one in which they are on opposite sides. In other words, kind of like our concepts of syn and anti that we've talked about before. And what's interesting is these 2 reduction products. So we have one in which the hydride adds from the reverse face of the plane, from the back face of the blackboard. One in which it adds from the front face of the blackboard. And what's interesting is these 2 products aren't formed in equal amounts. They're formed in a 72-to-28 ratio. So there's some stereoselectivity. There's almost 3-to-1 stereoselectivity. Now, I'm going to skip, because this is a short coverage of the topic, I'm going to skip over Donald Cram's model for the stereoselectivity, but I want to give you the widely accepted model because I think this is an important tool to have in our toolbox of understanding and beginning to think at the advanced level beyond sophomore organic chemistry. So the model is called the Felkin-Ahn Model. And I want to show you how we organize the substituents and why we can think in this way. So let us imagine some carbonyl compound with some alpha stereocenter, some stereocenter next to the carbonyl, with 3 different substituents. One of those substituents we'll call medium size, or R medium. One of those substituents we'll call large size, or R large. And one of those substituents we'll call small size, R small. In other words, like a methyl group, a cyclohexyl group, and a hydrogen over here. The hydrogen is small, the methyl group is medium, the cyclohexyl group is large. And the basic gist of what we're doing then is we are adding a nucleophile to the carbonyl compound. And the way we are going to think about this is that our main product is going to come so that our nucleophile is opposite the large group. And now what I want to do is to try to, so we've added in our nucleophile. What I want to do is to try to give us a framework for this. So let's do a Newman projection over here. Remember your Newman projections? In a Newman projection, you sight down a bond. So we're going to sight down the bond from the carbonyl group to the stereocenter. And so I'm going to go ahead and draw that on front. And the convention is when we draw a Newman projection, the group on front ends up being shown on the front atom. So this is the front carbon. This is the carbon that's the carbonyl carbon. And then we're going to project, or we're going to look down the bond here to the carbon bearing the stereocenter. And so I want us to think about our large group over here, our small group over here, and that's not so good. I'm trying to write 120-degree angles, so I'll do it a little bit better. Our small group and our medium group. And this is a very nice model to think about, because in this model, our nucleophile is going to come and it's going to overlap with pi star. Remember, all the formation of bonds that we talked about in our paracyclic chapter, particularly in electrocyclic reactions and particularly, I guess, cycloadditions, involves the overlap of a filled HOMO and a vacant LUMO. And so our nucleophile, with its lone pair of electrons, has a filled highest occupied molecular orbital. And the lobes of pi star sort of point out this way and out that way. And so we're going to come in on this Bürgi-Dunitz trajectory toward pi star and form a bond there. And once we form a bond and we go to a tetrahedral carbon, I will continue and now write an sp3 carbon, a Newman projection for an sp3 carbon. So here is now our R group. That would have been this group over here. I guess I should write it over here. And here is our nucleophile. And just to translate that in terms of what I've drawn over on this blackboard then, what we're saying is our model is we have our cyclohexyl here, our carbonyl here. In this particular case, we had a methyl group, right? It was a methyl ketone. And then on the carbon bearing the stereocenter, we have our hydrogen and our methyl. If I had started with the other enantiomer, in other words, the enantiomer with the methyl group over here and the hydrogen over here, then our nucleophile wouldn't have been able to add in like this. In that case, I would have had to rotate this group on the rear so that the cyclohexyl is down and the hydrogen and the methyl is over here. Or rather, I would have to rotate. I'm sorry, if I had the methyl, yeah, right, if I had the methyl here and the hydrogen here, I just rotate it so the carbonyl group is here and the methyl is there, and we get the enantiomer. So, okay, so our nucleophile comes in. Our nucleophile is a hydride in this case. And so that should be the product that gets us over to there. And if you want to see, just imagine here's our methyl group, our carbon bearing the oxygen. There's the carbon bearing the cyclohexyl group. There's the other carbon. I'll pick it up, bring it over. The cyclohexyl and the oxygen are on the same side, and they're pointing out.
If you wanted to use a bigger nucleophile, would it shift that even more, say like 80%?
Great question. If we had a bigger nucleophile like methyl lithium, would it shift the equilibrium to or the ratio to an even bigger selectivity? Most likely, because those steric interactions of the hydride coming in from this face versus the hydride coming in with the carbonyl rotated around and coming in, or, well, you could put it as the carbonyl, the nucleophile coming from this face, or the nucleophile coming from this face, or with it flipped around, the nucleophile banging into the methyl, those all become even worse. So yeah, you would predict very smartly you'd get even better stereoselectivity. Other questions? All right. In order to break these ideas down into bite-sized pieces, I have deliberately drawn a single enantiomer to start us out. Now I want to go ahead and just take sort of one more layer here just to better help us understand what really is being done. So keep in mind that this experiment doesn't have to be done with a pure enantiomer, and it wouldn't have been done with a pure enantiomer. It would have been done with a mixture of two enantiomers, i.e. the racemate, and the result is that you would get two diastereomers in 72 to 28 ratio. So let me unpack that and show you what I mean. In other words, if you envision the way Cram would have done this experiment, he would have done it with this compound, the racemic compound. The racemic compound, of course, is a 50-50 mixture, an equal mixture of the two enantiomers, the enantiomer in which the cyclohexyl group is out front, and the enantiomer in which the cyclohexyl group is in back. That, in turn, would have given the product in which the OH is syn to the cyclohexyl group from the first enantiomer and from the second enantiomer. And collectively, these two enantiomers would have been 72%. And then you would also have the product in which the hydride came from the other side. And again, this would be the two enantiomers. And those would have been our 28%. In other words, when I write this molecule and don't show a stereocenter, there is still a stereocenter here. And in fact, the molecule is a 50-50 mixture of this stereochemistry, which happens to be 1, 2, 3, happens to be the arc stereochemistry, and this stereochemistry, the S stereochemistry. The R enantiomer encounters hydride, and 72% of the R enantiomer partitions to this diastereomer, and 28% partitions to this diastereomer. The S enantiomer, an equal amount of it, encounters the nucleophile, encounters the hydride, and 72% of the S enantiomer partitions to this diastereomer, and 28% partitions to this diastereomer. So collectively, we get the racemic of what I will call the syn diastereomer as 78%, and collectively we get the racemic, what I'll call the anti-diastereomer, as 28%. And if you did this experiment and monitored by, let's say, GC, by gas chromatography, you would see one peak for the syn and one peak for the anti in 72 to 28% ratio. Thoughts? You look like you're taking it in.
I am a little confused because, I mean, the basic deciding factor of which enantiomer you get is which rotational conformation it's in at the time that the hydride moves in, right?
Ah, beautiful question. The question here was, what is the deciding factor? And so basically, the way to think about this is as follows. Imagine these two rotational states. All right. And these two rotational states are not equally populated, but they are both populated. So they are in rapid equilibrium. They are interconverting 10 to the 9th times per second, roughly, billion times per second. You have an activation barrier. The hydride collides with this state, and most of the time it says, I'm not reacting. Either it collides this way and it says, oh, the cyclohexyl group is too big, or, oop, the methyl group is this way, is too big. So most of the time coming in at the Burgi-Dunitz trajectory, it just turns up its nose and says, nuh-uh. The hydride collides with this rotational state, and it says more times than not, or at least more times than it does with this rotational state, oh goody, I can go ahead and overlap with pi star. It bounces in this way and it says, can't get in. So basically it has all of these ways that can come in, and most of the time, 72% of the time, it comes in this way because this is the lower energy path. To put it another way, we have all of these hypothetical transition states going from reactants to product, or reactant to the alkoxide. The lowest energy transition state is the transition state for hydride to come in this way. And so in most cases, it reacts that way. Good. And this is what we are taking in, and this is why this is an advanced level course. All right, I want to bring in one other concept. So this is what you call substrate base control of stereoselectivity. And I want to now just introduce the concept of reagent-based control of stereoselectivity. Not because I want to show you every possible example, but again, because I want you to understand the different issues we're dealing with. And this all falls into modern synthetic organic chemistry, which we are going to see more and more of in the subsequent chapters. So when we started talking about the reduction of, let's say, acetophenone with sodium borohydride, we had no stereoselectivity. In other words, we get both enantiomers. We have to get both enantiomers. In the absence of new chirality, we have no chiral preference. Sodium borohydride adds from both faces with equal probability. We get the racemate. Sodium hydride borohydride being achiral, half the time adds from the Ray face, half the time adds from the C face. But that game changes if we have a chiral reducing agent. So if we have a chiral reducing agent, now we can get selectivity. Now we can get one enantiomer or the other enantiomer with a significant preference. Not necessarily, as a matter of fact, never 100%, but a strong bias if you have a good chiral reducing agent, a strong bias for one enantiomer or the other. In other words, you can get the optically active alcohol. All right, and I want to give you one example of a chiral reducing agent. It's actually not a traditional borohydride, but it is a boron reagent. This was developed by H.C. Brown. H.C. Brown won the Nobel Prize for developing boron chemistry. He won the Nobel Prize in 1979. And two very useful reagents that he developed were, actually, I'm going to write this on the other board just because they're a little bit big. So I'm going to write them. They're derived from pinene. They're derived from pinene. Pinene is a terpene. Anyone know where you find pinene? Pine needles, pine bark, turpentine at the hardware store. And it turns out that with reasonable enantiomeric purity, one can get either enantiomer of pinene. And I kind of hinted at this before when I talked about Barry Sharpless's Nobel Prize winning work for asymmetric epoxidation, and I talked about tartrate. So you can get either enantiomer of pinene, not quite enantiopure, but you can go ahead and get the reagent pure. This reagent is called minus IPC, which is isopinyl camphenyl boron chloride, two isopinyl isopinenes on a boron chloride reagent. And this reagent here is the enantiomer. E.J. Corey, another Nobel Prize winner, has also developed various chiral boron reducing agents. And so I'm only going to show you these examples from H.C. Brown. And all I really want to do, these actually transfer a hydride from carbon, so they're not a borohydride reagent. We're not going to worry about the mechanism. All I want to do is show you the concept here. And the concept is that if we now take our acetophenone from the previous example and we treat it with 1 enantiomer, the minus enantiomer, minus means negative optical rotation. If we treat it with the minus enantiomer of IPC2 boron chloride, we get the S enantiomer. We get 98% EE of the S enantiomer. In other words, a 99:1 ratio of the S enantiomer. And conversely, if we take the same ketone, acetophenone, and we treat it with the plus enantiomer of IPC2 boron chloride, we get 98% EE of the R enantiomer. All right, now I thought that's a really useful sort of juxtaposition of the Cram concept, because the Cram concept says on the right conditions, you can go ahead and use one stereocenter in the molecule to build the next stereocenter. And the H.C. Brown concept here, so that's the substrate-based control. The reagent-based control says you can go ahead and use a reagent to pick which enantiomer you get. And where both of these have gone then is toward total synthesis of complex molecules, toward the development of catalytic rather than stoichiometric chiral systems so that you can catalytically use reagent-based control. Anyway, it's a fun area. All right, with that said, now I want to continue to play with this concept of alcohols, and I want us to play with stereochemistry and mechanism in some different ways. So I want to show what happens if you want to change a stereocenter. This is sort of a fun concept, and it brings in a nice mechanistically interesting reaction. Was there a question? All right. So I'm going to show us a particular molecule, a complex molecule, where we have several stereocenters in the molecule already set. And we have an alcohol. And I want to pose a question that came up in a synthesis. All right, what do you do if you want to swap one stereocenter? In other words, if you have one enantiomer of, or one, I should say, diastereomer at the alcohol position, and you want to go and invert that stereocenter. How do you do this? And the reaction that I want to show you is called the Mitsunobu reaction. Mitsunobu reaction involves an SN2 displacement where you activate the alcohol, you make it into a leaving group with phosphorus, with triphenylphosphine. Phosphorus loves oxygen. Once it gloms on to oxygen, once it forms a covalent bond to oxygen, it doesn't want to get released from oxygen. So the sequence of steps, and I'm going to write this in general, is you take the alcohol. Here's our OH. I'll draw it in the same stereochemistry. I'm just going to draw this in the abstract. So I'm going to draw this as R and R prime. We're going to take the alcohol. We're going to treat the alcohol with triphenylphosphine, PHP3, and a reagent called DED. I'll draw out DED in just a second. It's diethyl azodicarboxylate. And we're going to actually, for the sake of space, I'm just going to write it next to the triphenylphosphine. And then we're going to take some carboxylic acid. I'm going to take benzoic acid in this particular case. And the overall result is that the benzoic acid, or more specifically the benzoate, is going to do an SN2 displacement. The triphenylphosphine and DED will react to make this oxygen a leaving group with phosphorus. The carboxylate of benzoic acid will go ahead and make our carboxylate, and we're going to do an SN2 displacement with inversion of stereochemistry to make the corresponding ester. And then in a separate step, if you carry out hydrolysis with acid or base, in other words, in a separate step, then you will now get the corresponding alcohol. And so you can imagine this sequence: treat this complex molecule with triphenylphosphine, DED, and benzoic acid, get the corresponding benzoate, and then hydrolyze, although in this particular case, you'd also hydrolyze this methyl ester here, but then hydrolyze the corresponding compound, hydrolyze the ester to the corresponding alcohol. And the reagent DED, diethyl azodicarboxylate, is this compound here. It's an azo group with two esters on it, like so. And what I want to do now is to show you the mechanism for this reaction, because I think this ties in well to our concepts of curved arrows and arrow pushing. All right, one of the important ideas that we have been focusing on in this class and thinking about mechanisms is nucleophiles and electrophiles, and then reactions like aldol reactions we've talked about, and I think we've mentioned the Michael addition reaction as well, conjugate addition. So in other words, a nucleophile can attack not right at an electrophilic carbonyl group, but at a double bond conjugated. Often we see it as a carbon-carbon bond. So let us write out a mechanism, and I'm going to try to be on my best behavior for at least for the reacting centers, keeping track of our lone pairs of electrons. I will probably let them slip at other sites in the molecule. So here's our diethyl azodicarboxylate. Our triphenylphosphine is a nucleophile. Electrons flow from the lone pair on the nucleophile to the electrophile. You can write a variety of resonance structures for the resulting adduct. I am going to choose one of those resonance structures to write. like so. Oh yeah, and a positive charge on the phosphorus. Phosphorus, as I said before, phosphorus really likes oxygen. And so we can imagine our alcohol. And for now, I'll just shorthand the alcohol. We can imagine our alcohol, and I don't really care how you think about the reaction. I'm going to push my arrows this way. I'm going to envision the nitrogen with the negative charge taking off the proton on the alcohol, us forming a bond between oxygen and phosphorus, and us pushing electrons back on to nitrogen. Now, the main point here is that by activating the triphenylphosphine, by reacting with dead, we've now made the phosphorus electrophilic. The oxygen from the alcohol has now formed a bond to the phosphorus, and the overall result is that we have a good leaving group on the alcohol. I sort of packed up the alcohol structure on the previous panel there in order to go ahead and not show stereochemistry, just to get things written out, but now I'll go ahead and I'll show it. Let's just go ahead and finish up what we need to do first. All right, so at this point, we have a basic nitrogen on what's coming from our diethylase dicarboxylate. We have our acidic benzoic acid. So you get acid-base chemistry. Plus the benzoate anion. The benzoate anion is now going to serve as a nucleophile in SN2 displacement. So I'm going to draw out our alcohol. Now I'm going to show with full glory all the R groups and stereochemistry and so forth as we set ourselves up to go into our SN2 displacement. All right, so here's our alcohol with the phosphorus connected to it. In other words, the alcohol that is now prepared with a leaving group. Here's our benzoate anion. The benzoate anion is now set up for an SN2 reaction. We now invert our stereochemistry and form triphenylphosphine oxide. Yeah?
Can you do the same
Absolutely. Absolutely. So the question was very good. Couldn't we do the same inversion of stereochemistry with making the tosylate or the mesylate of the alcohol and then having a nucleophile like sodium benzoate doing the SN2 displacement? And so on paper, yes. In practice, the leaving group ability of the phosphorus oxygen bond is even better than the leaving group ability of the tosylate. So we generate a better leaving group. We are, in both cases, not well set up for, not going to have a lot of elimination reaction, but I think basically you would find that without a lot of heating, your carboxylate wouldn't be a good enough nucleophile, your benzoate wouldn't be a good enough nucleophile to rapidly displace tosylate or mesylate at a secondary center. Remember, secondary centers are slower than primary. If you say, I'm going to then amp up my nucleophile and go to an alkoxide, you're going to have more elimination reaction, E2 elimination, to form alkene. So in practice, the Mitsunobu is not only convenient because it's one pot, but it also gives a good chemical yield with fewer side reactions. Good question. And of course, this is part of the whole idea of synthetic organic chemistry is we've got this mechanistic framework understanding what's possible, helping us understand what's possible. And then we have the empirical realities that lead to, yes, it's possible, but in practice it doesn't, to want a better term, an engineering term, work very well when one tries to reduce it to practice in the laboratory. And so experiment ends up guiding us within this theoretical framework. Good question. All right, I want to show you one last set of reactions in this framework of alcohols and oxidation state. And I want to talk specifically about what happens when you have an alcohol and you want to get rid of it. You want to convert it to an alkyl group. Alcohols are great products of carbon-carbon bond-forming reactions. You add a Grignard reagent to a ketone, you get an alcohol. You formed a new carbon-carbon bond. Well, what if you wanted that carbon-carbon bond, but you no longer want the alcohol? In other words, that was just a passing point. This is not an uncommon situation in synthetic organic chemistry. And we'll see more of this as we move along into chapters 7 and 8. All right, I'm going to show you a complex molecule, a real complex molecule from a real synthesis. It's a synthetic intermediate. And what I want to do in this particular synthesis, we have a 7-membered ring fused onto a 5-membered ring. Or to put this into terms, we have a system that has 10 carbons in a bicyclic system. It is a bicyclo 5-3-0 decane system. And we want to take our alcohol in the bicyclo 5-3-0 decane system, and we want to get rid of it because now, let's say, in this particular series of synthetic transformations, it's no longer needed in the final product. And the reaction sequence I want to show you, which is cool because it brings up the theme of radical chemistry, is the Barton-McCombie deoxygenation. And the sequence of steps is you use a base like sodium hydride to pull off the alcohol group. You add the corresponding carboxylate into carbon disulfide, and then you treat with methyl iodide to get what's called a xanthate ester. And finally, you carry out a free radical reduction reaction with tributyl tin hydride. We've seen tributyl tin hydride and free radical chemistry already in the homework. You use tributyl tin hydride. We've talked about it in class. You heat with AIBN. AIBN is a radical initiator. And this overall sequence of formation of the alkoxide, formation of the xanthate ester, and free radical reaction with tributyl tin hydride gets rid of the alcohol group. And I think this is a nice place to conclude because it helps us see the basic processes of free radical mechanisms and reinforces some of the concepts from chapter 5. All right, so first step, alcohol plus sodium hydride. Everyone should remember sodium hydride is a base, not a reducing agent. Well, it is doing reducing, but it's not reducing carbonyls. Sodium hydride, NaH, that's a lousy N. NaH reacts with an alcohol to give the corresponding alkoxide salt. Sodium alkoxide salt. Plus, if I wanted to balance my equation, half a mole of hydrogen. Next, our alkoxide, RO-, adds into carbon disulfide. Carbon disulfide is isoelectronic with carbon dioxide. Sulfur is below oxygen in the periodic table. That adds in to give the corresponding thioanion, and the corresponding thioanion. Sulfur-based anions are fantastic nucleophiles, just wonderful nucleophiles in all sorts of SN2 reactions. Methyl iodide reacts readily with sulfur anions. We get RO, that's a lousy orientation here. Like so, we get the corresponding xanthate ester. All right, so that's step 2. Step 3, it's a free radical chain mechanism. Free radical chain, yeah.
Does it turn into the carbonyl or does it stay in the
Oh, thank you. No, we do not magically transmute sulfur into oxygen. Other questions? All right, free radical chain mechanism. The whole gist of free radical chain mechanisms is we have initiation steps to get the process going. Remember, AIBN transforms itself into the isobutyronitrile radical by loss of nitrogen. Isobutyronitrile radical reacts with tributyl tin hydride, abstracting a hydrogen. What I love about free radical chemistry is there aren't that many different reactions. There's atom abstraction, most often hydrogen atom abstraction, sometimes halogen atom abstraction. Hydrogen atom abstraction gets us to tributyl tin radical. The tributyl tin radical propagates the chain. And the chain runs dozens or hundreds of times before termination, before two radicals combine and recombine to form a new bond or disproportionate to pull off a hydrogen. So here's the chain propagation steps. It involves just 3 steps over and over again, and they all involve fundamental radical processes. So tin loves sulfur. In general, well, it's hard to generalize. Phosphorus loves oxygen, tin loves sulfur, so it's hard to say across rows of the periodic table. But in general, elements that are down outside the second row of the periodic table, below phosphorus, oxygen, nitrogen, and so forth, tend to have a good affinity for each other over elements that are in that second row. Okay, so we get fundamental radical step, addition to a double bond. We've seen it in our mechanism chapter. We get addition to the sulfur-carbon bond. To give a new free radical. The next step we get is fragmentation. Fragmentation is the opposite of addition. Mechanistic inverse of addition. In other words, we add to a pi bond to get a free radical. Here, the free radical kicks out, gives us back our pi bond. And the final step in this chain process is atom abstraction, specifically hydrogen atom abstraction. The free radical plucks off the hydride. This gives us our carbon-hydrogen bond plus a tributyl tin radical, and the chain continues. The tributyl tin radical reacts with another xanthate molecule. All right, we will pick up next time talking about Chapter 7, homeworks in the box up front, and I will see you at discussion, or Stan and Sebastian will see you at discussion this week.